बोर्डाच्या आपण महाराष्ट्र स्टेट बोर्डाच्या 12वीच्या सिलेबसप्रमाणे सर्क्युलर मोशन, फिजिक्समधला सर्क्युलर मोशन हा चॅप्टर डिटेल स्टडी करणार आहे. हा चॅप्टर स्टडी केल्यानंतर तुम्हाला सगळ्या बेसिक कन्सेप्ट सर्क्युलर मोशनमधल्या क्लिअर होतील. तसंच 12वीच्या सिलेबसप्रमाणे पूर्ण चॅप्टर मी कव्हर करणार आहे, तर याचा अभ्यास तुम्हाला व्यवस्थितपणे करता येईल. सुरुवातीला आपण काही बेसिक डेफिनेशन ज्या आवश्यक आहेत.
Now we study few basic definitions from circular motion which are necessary to understand the circular motion thoroughly. First definition: uniform circular motion. The motion of the particle along circumference of circle with constant speed is known as uniform circular motion. It is also abbreviated as UCM. Second definition: radius vector. It is also known as position vector. It is defined as the vector starting from center of the circle to position of the particle at any instant. It is known as radius vector, since it gives us the position of the particle at any instant, so it is also known as position vector. Third, linear velocity. The rate of change of linear displacement with respect to time is known as linear velocity. It is always denoted by v bar. V bar equal to ds bar upon dt. The SI unit of linear velocity is meter per second. Fourth definition: angular displacement. It is defined as the vector whose magnitude is angle described by radius vector when particle moves from one point to the other, and its direction is given by right hand thumb rule. It is always denoted by d theta bar. Pathway definition: angular velocity. The rate of change of angular displacement with respect to time is known as angular velocity. It is denoted by omega. Angular velocity is a vector quantity, so it is denoted by omega bar. This definition is similar to the linear velocity. So, in angular velocity, the term angular displacement is used. Rate of change of angular displacement with respect to time. Omega bar equal to d theta bar upon dt. Its SI unit is radian per second. Savi definition: angular acceleration. The rate of change of angular velocity with respect to time. It is always denoted by alpha bar, and alpha bar is given by alpha bar equal to d omega bar upon dt, where d omega bar is change in angular velocity in time interval dt. So alpha bar is given by d omega bar upon dt. SI unit of angular acceleration is radian per second square. Satvi definition: time period. It is defined as the time taken by particle performing UCM to complete one revolution. It is always denoted by capital T. Omega equal to d theta upon dt equal to 2 pi upon t, because in one complete rotation the angle described by particle is 360 degree. Angle described by radius vector is 360 degree or 2 pi radians. So omega equal to 2 pi upon capital T, since d theta is 2 pi and dt is nothing but capital T. So the time period is given by t equal to 2 pi by omega. पुढची definition, शेवटची. It is frequency. The frequency is defined as the number of revolutions completed by particle performing UCM in unit time. It is always denoted by n. So n equal to 1 upon t, reciprocal of time period. So SI unit of frequency is hertz or cycles per second. So omega equal to Omega is nothing but 2 pi upon t. 1 upon t is nothing but n. Therefore, omega equal to 2 pi n.
Now we are going to study the relation between linear and angular velocities. Consider a particle performing UCM along the circumference of radius r in anticlockwise sense. Initially, the particle is at point P, and in time interval dt it moves from point P to point Q, so that radius vector rotated through angle d theta. If linear displacement is ds bar and angular displacement vector is d theta bar, then according to definitions of linear and angular velocities, v bar is equal to ds bar upon dt. According to definition of angular velocity omega bar, it is given by omega bar equal to d theta bar upon dt. Say this is equation 2. According to above vector diagram, linear displacement vector ds bar, angular displacement vector d theta bar, and radius vector r bar are related by vector equation ds bar equal to d theta bar cross r bar. This equation is obtained by using right hand thumb rule. This is equation 3. Dividing on both sides with dt, we get ds bar upon dt equal to d theta bar upon dt into r bar. From equations 1 and 2, ds bar upon dt is velocity vector v bar, linear velocity vector, and d theta bar upon dt is angular velocity vector omega bar. Therefore, we get v bar equal to omega bar cross r bar. This is the cross product, example of cross product, omega bar cross r bar. To obtain the scalar relation, we write v equal to omega into r into sin 90, because omega bar and r bar are always perpendicular to each other. So angle between them is 90 degree. So v equal to omega into r into sin 90, where omega and r are magnitudes of angular velocity and radius vector. Sin 90 is nothing but 1. Therefore, the scalar relation between linear and angular velocity becomes v equal to omega into r. Now we are going to study the next article, acceleration introduced in particle revolving in uniform circular motion. When particle is revolving along the circumference of circle with constant speed, the direction of motion changes continuously. Due to this change in direction of motion, the velocity vector also changes continuously. Since velocity vector changes, the acceleration is introduced in the particle due to change in velocity vector. This we are going to obtain the expression for this acceleration, which is introduced in a particle performing UCM due to change in direction of motion. For this, consider a particle performing UCM in anticlockwise sense as shown in figure. When particle rotated through angle theta, it moves to point P and the radius vector is r bar. This radius vector r bar is resolved into two mutually perpendicular components. Along x direction, the component is r cos theta, and along y direction, component is r sin theta. Obtained as r bar equal to I bar into r cos theta plus j bar into r sin theta. So here r bar equal to small r into I cos theta plus j sin theta. So left hand side of this equation 1 gives us the radius vector r bar, and right hand side is split into two parts. R is the magnitude of vector r bar, and I cos theta plus j sin theta is gives the direction of vector r bar. So r bar equal to r into I bar cos theta plus j bar sin theta. According to definition of velocity, velocity is given by ds bar upon dt. V bar equal to ds bar upon dt, which is same as the dr bar upon dt. So V bar equal to differentiation d by dt of r bar. R bar is given by equation 1. So V bar equal to d by dt of this r bar is nothing but r into I cos theta plus j sin theta. So V bar equal to, solving this, we get equation V bar equal to r into I into differentiation of cos omega t plus r into j differentiation of sin omega t. Since theta equal to omega into t, the particle is revolving with constant angular velocity omega. So finally we get V bar equal to r into I bar d by dt of cos omega t plus r into j bar d by dt of sin omega t. Differentiating with respect to t, we get V bar equal to r into I into minus sin omega t into omega plus r into j into cos omega t into omega. So here V bar equal to r omega into minus I bar sin omega t plus j bar cos omega t. Here again, this equation, left hand side of equation 2 gives us the velocity vector at point P. So velocity vector, right hand side gives us the magnitude of velocity r omega into bracketed quantity gives us the direction of linear velocity. So magnitude and direction, we split the vector on right hand side in magnitude and direction. This equation gives the velocity of particle at point P. According to definition of acceleration, actually we have to find the acceleration introduced in a particle performing UCM due to its change in direction of motion. So acceleration is given by dv bar upon dt, which is equal to d by dt of v bar. V bar right hand side is r omega into minus I bar sin omega t plus j bar cos omega t. A bar is given by minus r omega I bar cos omega t into omega plus r omega j bar minus sin omega d into omega. So this equation can be expressed as A bar equal to minus r omega square into I cos omega t plus j sin omega t. But from equation 1, r into I bar cos omega t plus j bar sin omega t is nothing but r bar. Therefore, the same equation can be written as A bar equal to minus r bar into omega square or minus omega square r bar. This equation gives the acceleration introduced in a particle performing UCM due to change in direction of motion. Negative sign indicates that the direction of acceleration is opposite than radius vector r bar. That is, the direction of acceleration is towards the center of circle. Therefore, this acceleration is known as centripetal acceleration or radial acceleration, and its magnitude is given by a equal to uh, v square upon r or r omega square. Now we are going to study the centripetal and centrifugal forces. When particle is revolving along the circumference of circle with constant speed, its direction of motion changes continuously. Due to change in direction of motion, its velocity vector changes, and due to change in velocity, acceleration is introduced in the particle. This acceleration is always directed toward the center of the circle, so it is known as centripetal acceleration. And according to Newton's second law of motion, the centri forces come into existence. This force is known as centripetal force. The centripetal force is also directed toward the center of the circle. The magnitude of centripetal force is obtained by Newton's second law of motion. Force equal to mass into centripetal acceleration. So mass, if particle mass is m, then F equal to m into centripetal acceleration is v square by r or r omega square. Therefore, the centripetal force is always given by mv square upon r or mr omega square. So this centripetal force is always directed toward the center. Therefore, it is known as centripetal force. The centripetal force is always provided by some external force. For example, when stone is tied to one end of a string and rotated in a horizontal circle, in that case, tension in the string provides the necessary centripetal force. So tension is the external force which provides the centripetal force. Second example, satellite revolving around the earth. The gravitational force of earth acting on satellite provides the necessary centripetal force. So here gravitational force is the external force which provides the necessary centripetal force. So in general, for any circular motion, the external force, some external force provides the necessary centripetal force. Centrifugal force. When in circular motion, centripetal force is not provided by any external force, then a pseudo force is come into existence which is directed away from center of the circle. So this pseudo force is known as centrifugal force. It is hypothetical force. Its magnitude is same as centripetal force, and it is not provided by any external force. So centrifugal force has also the same magnitude as centripetal force, that is mv square upon r or mr omega square. Centrifugal force is pseudo force, it is not a real force. Distinction between centripetal force and centrifugal force. First, centripetal force is a real force, centrifugal force is a pseudo force. Second, centripetal force is directed towards center of the circle, whereas centrifugal force is directed away from center of the circle. Third, centripetal force is provided by some external force. Centrifugal force is not provided by any external force. And fourth, centripetal force is a real force in inertial frame of reference, whereas Centrifugal force is real force in non-inertial frame of reference. Now we are going to study the applications of circular motion. First application, banking of roads. बँकिंग याचा अर्थ काय? बँकिंग म्हणजे व्हेकल रोडवरून चाललेला असताना रोडला जर टर्न आला तर टर्नला बाहेरची बाजू थोडीशी वरती उचललेली असते आणि आतल्या बाजूपेक्षा, त्यामुळे रोड हा स्लँटिंग होतो थोडासा. ही जी अरेंजमेंट आहे रोडची याला बँकिंग ऑफ रोड्स म्हणतात. To avoid the skidding and to make turning safer of fast moving vehicles, usually the outer edge of the road is slightly raised above the inner edge. This arrangement of road is known as banking of roads, and the angle through which outer edge is raised above the inner edge is known as angle of banking. It is always denoted by theta. When vehicle is moving on such a banked road, then necessary centripetal force is provided by component of normal reaction and component of frictional force. Necessity of banking. When vehicle is traveling along curved horizontal road, not banked, then necessary centripetal force is provided by only frictional force, and we are totally relied on friction. When roads are wet and slippery, or when tires of the vehicle are worn out, then necessary centripetal force is not available from force of friction and vehicle may skid outside. To avoid this skidding, usually roads are banked. Then component of normal reaction and horizontal component of friction provides necessary centripetal force. Now we obtain the expression for maximum safe speed and angle of banking of road. For that, consider a vehicle negotiating a right turn on curved banked road. The vertical section of vehicle and road surface is shown in the figure. Different forces acting on a vehicle are: first, weight mg acting through cg in vertically downward direction. Second, normal reaction n acting perpendicular to the road surface. This normal reaction is resolved into two components. Vertical component is n cos theta because this angle is theta. Here normal reaction is perpendicular to road surface and vertical component is perpendicular to the horizontal. So this angle is theta. The normal reaction n is resolved into two components. This opposite component is n sin theta, which is same as this, and vertical component is n cos theta. The frictional force Fs is acting along the road surface in downward direction. So frictional force is also resolved into two components. First, horizontal component Fs cos theta and vertical component Fs sin theta. Okay. Fs sin theta is directed downwards. Okay. The normal reaction is resolved into two components, n cos theta and n sin theta. Frictional force is also resolved into two components, Fs cos theta and Fs sin theta. Balancing different forces acting on vehicle in vertical and horizontal directions. So in horizontal direction, the centripetal force mv square upon r is provided by n sin theta plus fs cos theta. In vertical direction, mg plus fn sin theta equal to n cos theta. This equation can also be written as mg equal to n cos theta minus fs sin theta. Dividing equation 1 by equation 2, we get left hand side v square upon rg, m gets cancelled, equal to n sin theta plus fs cos theta divided by n cos theta minus fs sin theta. But fs is nothing but mu s into n. N is normal reaction and mu s is coefficient of static friction between road surface and tires of the vehicle. So v square upon rg equal to n sin theta plus mu s into n cos theta divided by n cos theta minus mu s into n sin theta. So here n gets cancelled and we get v square upon rg equal to sin theta plus mu s cos theta divided by cos theta minus mu s sin theta. Dividing on both sides by cos theta, we get v square upon rg equals, here sin theta upon cos theta becomes tan theta, mu s cos theta upon cos theta becomes mu s, divided by cos theta upon cos theta is 1 and minus mu s sin theta upon cos theta is nothing but mu s tan theta. So we get v square equal to, this rg comes over here, rg into tan theta plus mu s upon 1 minus mu s tan theta, or v equal to square root of rg into tan theta plus mu s upon 1 minus mu s tan theta. This equation gives the maximum safe velocity of the vehicle traveling along curved banked road. कर्व्ड बँक्ड रोडवरून व्हेकल जात असताना ते मॅक्सिमम किती सेफ स्पीडनी जाईल हे सांगण्याचं काम हे इक्वेशन करतं. एक्सप्रेशन फॉर अँगल ऑफ बँकिंग. Angle of banking. When coefficient of friction between tires and road surface is 0, then the above equation becomes V equal to square root of Rg tan theta, or V square equal to Rg tan theta. So tan theta equal to V square upon Rg. Then theta is given by theta equal to tan inverse of V square upon Rg. So this equation gives the angle of banking of the road. रोड कन्स्ट्रक्ट करत असताना किती अँगल ठेवायचा बँकिंगचा हे ठरवण्याकरता या इक्वेशनचा वापर होतो. थीटा इक्वल टू टॅन इनवर्स ऑफ व्ही स्क्वेअर अपॉन आर जी. Next article, we are going to study the conical pendulum. Conical pendulum is defined as the simple pendulum whose bob is revolving in horizontal circle with constant speed and string makes certain angle with the vertical. This is known as the conical pendulum. In conical pendulum, different forces acting on pendulum on bob are: first, weight mg is acting in vertically downward direction and tension in the string T acting along AO. The tension T is resolved into two components. Vertical component T cos theta, which balances weight mg, and horizontal component T sin theta. provides the necessary centripetal force acting towards the center of the circle. Derivation of velocity and time period. Consider a conical pendulum revolving in horizontal circle with constant speed v as shown in above figure. The different forces acting on bob are: first, weight mg acting in vertically downward direction; second, tension T acting along the string along AO. Tension is resolved into two components. T cos theta is vertical component and T sin theta in horizontal direction, horizontal component, which provides the necessary centripetal force. T cos theta balances weight mg. So balancing in horizontal and vertical directions, we get mv square upon r equal to T sin theta, horizontal component. So centripetal force is provided by T sin theta. And second, weight of the bob is balances by T cos theta. So mg equal to T cos theta. Dividing equation 1 by 2, we get v square upon rg equal to tan theta, or v square equal to rg tan theta. So v equal to square root of rg tan theta. This equation gives the horizontal velocity of the bob of conical pendulum. The angle theta made by string with the vertical is given by theta equal to tan inverse of v square upon rg. Now we are obtained the expression for time period of conical pendulum. It is denoted by T dash. Since we denoted T, we use T for tension in the string. Here for time period we use T dash. We know that velocity of conical pendulum, bob of a conical pendulum, is given by root rg tan theta. But velocity is also given by distance upon time. That is, in one complete rotation, the distance travelled is 2 pi r and time required is known as time period, T dash. So V is also equal to 2 pi r upon T dash. Now, comparing right hand sides of these two equations, we get 2 pi r upon V is equal to 2 pi r divided by root rg tan theta. If r is taken inside, then root r square upon rg tan theta. This becomes, or we simplify it as T dash equal to 2 pi into square root of r cos theta divided by g sin theta. That is 2 pi into square root of L sin theta upon g tan theta. When tan theta, we substitute sin theta upon cos theta. Sin theta gets cancelled and we get the expression T dash equal to 2 pi square root of L cos theta upon g. This equation gives the time period of conical pendulum, where L is length of the string, theta is angle made by string with the vertical, g is acceleration due to gravity. So all are known quantities. So time period is given by this equation, 2 pi equal to square root of L cos theta upon g. Now we study next article, that vertical circular motion. First we determine the velocity of particle moving in vertical circle. Initially the motion in vertical circle is not uniform. This is the example of non-uniform circular motion, because when particle is moving from lowest point to highest point, then acceleration due to gravity is acting in vertically downward direction. Therefore, velocity of particle is goes on decreasing. Here velocity decreases continuously while moving in upward direction. At highest point the velocity is minimum, and when particle is descending down, then acceleration due to gravity is also in downward direction. Therefore, velocity goes on increasing. Velocity here increases continuously and it becomes maximum at lowest point. So here at lowest point velocity is highest, at point C midpoint velocity is intermediate, and at highest point A velocity is minimum. So here we assume that at highest point A velocity is v1, at lowest point B velocity is v2, and at midpoint velocity is v3. Okay. We are going to determine the expressions for these three velocities. Let m be the particle of mass, then weight acting on the particle is mg. Tension in the string is T1. Then mg provides the necessary centripetal force required for circular motion of the particle at highest point. So at highest point centripetal force is mv1 square upon r equal to mg, where v1 is velocity of the particle at highest point. Since mv1 square upon r equal to mg, here solving we get v1 equal to square root of rg, where r is radius of the vertical circle and g is acceleration due to gravity. This equation gives the velocity at highest point A. Then velocity of lowest point B is obtained by comparing the total energy. The total energy at B is equal to total energy at A. The total energy is always given by kinetic energy plus potential energy at point B. So similarly, at point A, the kinetic energy plus potential energy. The kinetic energy at point B is given by half mv2 square, where v2 is velocity of the particle at lowest point B, plus potential energy is mgh. At lowest point h is 0. Therefore, mg into 0, that becomes 0, equal to kinetic energy of particle at point A is half mv1 square, where v1 is velocity of the particle at highest point A. Similarly, at highest point the height of the particle is 2r, 2 times radius from lowest point. Therefore, potential energy is given by mg into 2r. Solving, we get half mv2 square equal to half m into root rg bracket square plus 2 mgr. So here rg, it becomes rg. So half mrg plus 2 mgr, that is nothing but 5 by 2 mgr. But by cancelling m on both sides, we get half V2 square equal to 5 by 2 gr, or V2 square equal to 5 gr or 5 rg. Then V2 is given by square root of 5 rg. So this equation gives the velocity of the particle at lowest point, which is the maximum in entire circle, vertical circle. So this equation gives us the velocity of the particle at lowest point B. Now we obtain the velocity of particle at midpoint C. We compare again the energy at point C and at point B. Energy at C equal to energy at B. Kinetic energy at point C plus potential energy at point C equal to kinetic energy at point B plus potential energy at point B. Half mv3 square is kinetic energy at point C plus mg into r. So at point C, height of the particle is r from lowest point. So therefore potential energy is mgr, which is equal to half mv2 square. V2 is the velocity of the particle at point B. So this gives kinetic energy at point B plus potential energy at B is mg into 0, since height is 0 at point B. So we get, solving, half mv3 square equal to, here mgr plus half m into square root of 5 rg square, okay, plus mg into 0. This negative sign is due to this term is shifted from left hand side to right hand side. Okay. Then half mv3 square equal to 1 by 2 into 5 mgr minus this mgr. So we get half no, v3 square equal to 3 mgr, or v3 equal to square root of 3 rg. This equation gives the velocity of particle moving in vertical circle at midpoint C. Next, expression for tensions at different points in vertical circle. For that, consider a particle moving in vertical circle such that particle just passes highest point without slackening the string. So here at points A, B, C, the equations are: tension is acting in same direction as weight. So T1 plus mg, that must be equal to mv1 square upon r. Second, T2 is acting in direction opposite to mg. So T2 minus mg must provide the centripetal force, mv2 square upon r. And third, at point C, T3 is the tension which is directed toward the center. So T3 equal to mv3 square upon r. So these are the equations of tensions at 3 points A, B and C. We have already determined the velocities v1, v2 and v3 at 3 points. v1 is given by square root of rg, v2 is given by square root of 5 rg, and v3 is given by square root of 3 rg. Substituting these values in equations 1, 2 and 3, then we get first T1 equal to m into square root of Rg bracket square divided by R minus Mg. So it remains Mg only. Mg minus Mg equal to 0. So tension acting at highest point T1 is 0. Now T2 equal to M into 5Rg divided by R is nothing but 5 mg plus mg gets 6 mg. A 5Rg is nothing but V2 square. So tension at lowest point is highest and it is 6 mg. T3 equal to M into 3Rg divided by R. That is the tension at midpoint T3 is given by 3 mg. These equations give the tension at different points in vertical circle when it completes the vertical circle, just completes the vertical circle at highest point.